So it's time to start day 3 NVMSA. So thank you for joining this invited talk, day 3 NVMSA. I'm Hiroshi Nakamura, chairing this session. And it's my great pleasure to welcome 3 distinguished speakers. And the title of this session is Academic Research Centers of Excellence on Semiconductor in Japan. And the first speaker is Professor Tetsuo Endo. And let me introduce Professor Endo. Dr. Tetsuo Endo joined the ULSI Research Center Toshiba Company in 1987 and was engaged in the R&D and mass production of NAND memory. He became a lecturer at the Research Institute of Electrical Communication, Tohoku University in 1995. And now he is a professor at the Graduate School of Engineering. Director of the Center for Innovative Integrated Electronic Systems, and Deputy Director of the Center for Science and Innovation in Spintronics of Tohoku University. He received the 14th Prime Minister's Award for his contribution to industry, academia, government collaboration in 2016. And he received National Invention Award, the 21st Century Encouragement of Invention Prize for contribution to invention of 3D NAND memory in 2017. So, Professor Endo, please start your presentation.
Yes, thank you very much, kind introduction. First of all, thank you for all program committee and Nakamura Sensei for inviting me to this NVMSA 2022. Good morning, everyone. I'm Tetsuo Endo from Tohoku University. I'd like to share my material. So, can you see, right?
Yes, we can.
We can. Great honor to able to speak to you today. In this presentation, I'm going to talk about recent progress in spintronics-based low power LSI for carbon neutral society, from STT and SOT-MRAM to the AI IoT processor. So let's start from the background. Since the introduction of the perceptron in 1965, computer power was double every year until around 2010. However, due to the recent new applications, such as big data system, AI system, 5 system, and so on, the processing power from the 2010 to the 2020 is growing about 10 times per year, more than 5 times faster than Moore's law, as shown in this figure. Therefore, this recent rapid demand for the computing power cannot be achieved by only Moore's law. Therefore, on the other hand, we look for the carbon neutral society. For this, low power computing and low power LSI should be developed. As you can see, however, the power consumption was increased to order to several 100 watt now. For achieving future high PC, high performance computing, high level power management is one of the important technology. So I believe non-volatile logic chip that was a non-volatile function is a good way for low power system. This situation of the memory is about same. From viewpoint this, the emerging non-volatile memory such as the RRAM, PCRAM, and of course the MRAM are being actively developed. As you can see, the MRAM, my position is that MRAM is the best choice for the working memory application such as the SRAM and logic and DRAM due to its excellent endurance and compatibility with the CMOS, such as the writing voltage. So I'd like to show you the two kind of the way in MRAM. This table summarizes the motivation and the issue of the STT-MRAM and SOT-MRAM. STT-MRAM is suitable for the large capacity memory because it's simple cell structure. Therefore, the STT-MRAM was ready for the mass production earlier from the TSMC and Samsung Foundry and so on. However, high-speed operation is difficult due to the read and write disturbance. Furthermore, for achieving the scale down beyond 20 nanometer, it is still need to develop advanced MTJ stack technology with a higher thermal stability factor and advanced integration process, including the patterning technology. On the other hand, SOT-MRAM is suitable for the high-speed operation because it's wide operation margin. However, cell size is still a bit large due to its complex structure with 2 transistors and 1 MTJ. Furthermore, the STT-MRAM is still R&D phase. In order to realize the practical usage of the SOT-MRAM, it is needed to develop advanced SOT-MRAM technology and its integration process technology under the 300mm line. So next, I'd like to move to the STT-MRAM part. We already well known this like the double interface perpendicular MTJ. This technology is developed by the Tohoku University, the Ono Sensei group. This MTJ technology became today's de facto standard technology of the STT-MRAM. I already well known in the TSMC and Samsung Foundry started the STT-MRAM mass production with this double interface perpendicular MTJ technology. However, in case of the 20 nanometer generation, double interface perpendicular MTJ, its thermal stability is about 50. So it is not so good number for the non-volatile memory. So double interface perpendicular MTJ has still remaining issue for future scaling, in particular beyond the 20 nanometer generation. For overcome this issue, our team is proposed the quad interface MTJ technology, especially for achieving the advanced scalable MTJ technology with basically the same material set and the same cell structure of the current STT-MRAM. We propose a quad type the cobalt ion ball MGO interface MTJ and demonstrating its high performance. Thanks to the large number of this cobalt ion ball MGO interface, here is 1, 2, 3, 4, and quad MTJ achieved twice larger perpendicular entropy, resulting in twice higher thermal stability with keeping the same light current in comparison with the conventional double interface MTJ. Therefore, I think the quad perpendicular MTJ expected to apply to 1x nanometer generation. I'll show you the experimental result of our quad type and interface MTJ. As shown in these 10 photographs, we successfully fabricate the quad interface MTJ under the 300mm process line in Tohoku University. So as you can see, in the quad MTJ, the MGO cap, middle MGO, and MGO barrier layer were clearly observed on continuous white line. We also demonstrate that the further small MTJ size, such as 3x nanometer, The quad MTJ showed about 2 times larger thermal stability factor than that of the conventional double MTJ. In addition, in explorated the thermal stability of the quad MTJ chip is a 10 yield, that 10 yield rotation under the 16 nanometer size. Next, let me show you the result of the TMR ratio of the quad and double perpendicular MTJ. And here is the summary for the comparison with the TMR ratio versus the RA plot of the quad and double perpendicular MTJ. As you can see, more than the 2 times TMR ratio was achieved in the quad interface perpendicular MTJ at the 5 ohm square. To obtain these results, we have developed a new process for the MGO barrier and the high force free layer. Next, we evaluated CD and the dependency of the light efficiency at the 10 nanosec light pulse. Thanks to the higher thermal stability and the suppression of the lighting current at 10 nanosec for the quad interface MTJ. This is the light efficiency of the quad MTJ was improved by the factor of about 2 at 10 nanosec light operation until the 3x nanometer duration. Finally, I show you its endurance result of the quad MTJ technology. We investigated the endurance characteristics in the quad MTJ, which is the impact for the differential from the one order from the other non-volatile memory. I show in this result. This 80 nanometer quad MTJ and 33 nanometer quad MTJ achieved over 10/11 endurance while maintaining the 10-year retention due to its higher light efficiency than the conventional double interface. This is a very important result for the future STT-MRAM. So finally, I show you the scalability of the quad MTJ technology. In this study, we demonstrated that the advanced quad type MTJ enable us to realize over the diameter issue beyond 22x nanometer. In other words, this quad MTJ technology will contribute to the 1x nanometer STT-MRAM available for the wide application from the SRAM application and the embedded DRAM application, and of course including the embedded flash replacement application. So next, I'd like to move to the next topics. It's SOT-M. I already explained to you the SOT-MRAM uses a 3-terminal cell structure. Here is the read port. This 2 port is for the write port. This is a dual port device, right? So to realize the fast switching without external and magnetic field in SOT-MRAM, the many structures were proposed. For example, the IBEC group proposed a cobalt hard mask on the SOT device with a perpendicular MTJ. The Tohoku University group proposed, shown here, that by counting the in-plane magnetic MTJ related to the SOT channel line, the field free, and by this the field free and fast switching were realized at the same time. We call this SOT-MRAM structure counted SOT-MRAM. Our counted SOT-MRAM structure is simple. It merits the device structure is simple because the external mask is no need. So the first I examined the switching reliability for the counted SOT device until the sub-nanosec writing region. This figure, the left shows you the schematic of our measurement system for the counted SOT device. The right figure shows you the switching probability as a function of the applied voltage when writing pulse width the wide from the roughly the 10 nanosec to the 350 picosec. As you can see, the reliable switching at the switching probability of the 100% was realized for the fabricated counted SOT device. At the time, the champion data is our developed counting device. The switching the reliable when the writing pulse was down to the 0.35 nanosecond. This like the 2.2 gigahertz access latency is very important the performance for the high-speed non-volatile memory application. So next, I evaluate the thermal stability factor of the fabricated counted device as shown here. A large thermal stability factor of 70 at room temperature was obtained from the thanks to the low damage alloy technology at first in the world. This value is enough value, large value for the non-volatile memory, which required more than 10 years of the retention. And next, this slide shows the switching properties of the fabricated SOT-MRAM cell. SOT-MRAM cell meaning the SOT cell and the CMOS transistor are successfully integrated. These two figures show the left show the circuit diagram of the SOT-MRAM and the timing chart of the measurement. The counted SOT-MRAM cell is constructed with one SOT device and two transistors. Here, two transistors, which is the right operation mode and the read operation mode are selected. As you can see in the right figure here, so the counted SOT-MRAM successfully achieved the 10 nanosec vibrated writing. So this write speed of 10 nanosec is limited by the 55 nanometer CMOS transistor performance. Therefore, by using the more leading edge transistor, the CMOS transistor, the SOT-MRAM cell will be achieved to the 2.9 gigahertz operation. Moreover, the stable read operation was achieved. Finally, this shows you the prototype, the fabricated 4 kilobyte SOT-MRAM chip. It's a first result in the world. So this chip is fabricated by the hybrid process technology of the 55 nanometer CMOS and counted SOT MGJ made on the 300 millimeter wafer fabrication line in Tohoku University. In real-life fast switching without magnetic field, our developed SOT device with adopted in this design. This SOT-MRAM support the read mode and of the 32-bit bandwidth and the write mode of the 8, 16, 24, 32-bit variable bandwidth, as well as the synchronous read during write mode. This like the dual mode at the MRAM is the first result in the world. Now, finally, I'd like to move to the final topics, the AI and IoT processor. Today, we have enough time. I'd like to focus to the AI processor. For achieving the low power logic, the MTJ CMOS hybrid technology is very important thanks to its excellent power management. As shown in this figure, this slide, regarding to our fabricated chip result, 2-order power reduction is realized with MTJ CMOS hybrid technology in many kind of the application from the memory and TCAM, FPGA, micron. The low power logic with the MTJ CMOS hybrid technology brings accelerated of the IoT system, AI system, and three heterogeneous integration, such as the chiplet system, thanks to the suppression of the power density of the module. So I'd like to discuss the technology candidate for the AI processor. So the AI processor requires a high-level fusion system between the remembrance and judgment. Of course, the remembrance is covered by the non-volatile memory, and judgment is covered by CMOS technology. Therefore, for the AI processor requires a high-level fusion system between the non-volatile memory and the CMOS circuit. Especially the deep learning is a very important function to the AI system. Therefore, the deep learning requires a tough endurance to the non-volatile memory. From viewpoint is what kind of the non-volatile memory is the best in the AI system. And my position is Spintronics, the STT-MRAM and the SOT-MRAM, the best choice for this application. It's because from viewpoint is the low power and the high speed, and the deep learning is the STT-MRAM, the SOT-MRAM, the deep learning performance is the best. And for the non-volatile is important. Therefore, the SOT-MRAM is the best choice for the non-volatile brain inspired processor. So today, I'd like to focus to the top-down approach, the brain computing approach, embedded the information processing in the brain. So that I have enough time. Therefore, I show you only the result. So that this shows the photograph of the specification of our developed the movie associated processor under the 19 nanometer CMOS and 17 nanometer patent MTJ hybrid process. This chip is fabricated by the 12 core unit. And please focus to its average power. Our chip is the power consumption is only 600 microwatt. Therefore, in other words, our chip is achieved to the 30 microwatt per megahertz. This is roughly the 3-order power reduction is realized. For example, in comparison with a tensor processor from the Google. So I show you the demonstration result of our developed the AI chip. As shown in the result, the blue line is a case of the stone, the red line is a case of the wood stone target. As shown in this result, our developed associated processor is successfully find the stone and wood pattern respectively. Therefore, this AI processor is enough performance for the AI associated the function. So, moreover, I summarize this slide and show you the benchmarking result between the STT-MRAM based associated processor and the SRAM based CMOS based one. As shown in this figure, by using the CMOS MTJ hybrid technology, including the STT-MRAM, and the die size can be suppressed by 1 order, and the power consumption can be suppressed 3 order. This is a very important point for the future AI processor. Finally, I'd like to conclude my talk. So for next generation, the MRAM, we have successfully developed advanced STT-MRAM and SOT-MRAM technology, such as the novel quad interface MTJ and canted SOT device and our 300mm process line. And moreover, with our CIS novel technology, more reliable, the more stable STT-MRAM and higher speed SOT-MRAM will be realized. By this, the more low power LSI application, such as the AI processor and the IoT processor, will be open. However, as you know, Spintronics, MRAM, already become to the real technology from here. For for example, the smartwatch, or many smartwatch already enjoyed MRAM technology in the mass production. However, more innovative technology of the Spintronics device itself and its application technology, including the circuit and the architecture, are needed for future industry. For this industrial demand, the Tohoku University start new project as shown here. The project name is the Innovative Spintronics X Semiconductor Research Hub from the organized director is me. In this session, in this project, we will put the Spintronics, which is a game-change technology for the power saving of the integrated circuit by the Japan at the core. We will comprehensively conduct from the R&D of the new material and the device and the device R&D of the circuit architecture and the integration technology. That brings us the characteristic to the prototype verification to the power saving semiconductor chip. That accelerated the development of the CMOS semiconductor with collaborative and cooperation organization. So please hope, if we have a chance, please, I'd like to hope to collaborate everyone. Finally, the SOT-MRAM and its non-volatile processor will open a new application, as shown here. I believe this technology opened a new low power application from the IoT and the automotive security and edge system AI, of course, including the home electronic system. This is my acknowledgement for our work. Thank you very much. And that's all. Thank you.
Thank you very much, Professor Endo. So now this session is open for questions. Is there any questions? So yeah, how can I control this question? So Professor, can you see the chat?
Please, therefore, please wait. I stop to my video. I try to check chat. Okay. So the first question from thank you for impressive speed. I have several questions about SOT-MRAM. What is the most significant advantage of SOT-MRAM compared to the emerging such as SOT-MRAM? Yeah, of course. The SOT-MRAM, the merit is it's a high speed writing speed. Today, I'd like to show you the 350 picosecond writing speed by using the SOT-MRAM. Still, this SOT-MRAM keeps the 10-year retention performance. It's a non-volatile memory. I think as you know, the writing speed and non-volatile memory, the performance is have a trade-off. Therefore, the SOT-MRAM is the most important merit is its high-speed write speed. The high-speed write speed. So, moreover, the endurance is theoretically infinite. 10^20 or the 10^15. This tough endurance also the more important merit in person with another non-volatile memory. So if it's okay. So the second question is interested with quad MTJ, quad type MTJ. I think in redirect inference because we are under the quad MTJ interface. Yes. How do you deal with the interference issue? Okay, I already checked the quad MTJ, the interference the issue, and by using the LLG simulation. By this, until the 10 nanometer duration, this interference effect is no problem. Therefore, I think at least the 10 nanometer or the 8 nanometer generation, everybody fully enjoy the quad MTJ technology. It is my comment. what about the electromagnetic induction attack? No. So the Nakamura sensei, time is already coming. So I'd like to.
That time is almost coming. So,
if possible, Tanimoto-san, if possible, that I'd like to discuss later.
Yeah.
Great.
And also, you missed the second question. Second question is, so what is the most significant advantage of SOT-MRAM compared with other MRAM? Yeah.
Yeah. So the advantage is the high speed, for example, the high speed cache application. Therefore, as you know, the fast cache memory is in the CMOS the CMOS type SRAM for achieving the high speed cache. The 10 transistor, more 10 transistor is used. Therefore, the cell size is no problem. The high speed is very important for the fast cache application. Therefore, the SOT-MRAM have a chance to try to the fast cache replacement application. This is my opinion.
Okay, thank you, Professor. And also, time is running out, so I'd like to proceed to the next talk. So thank you, very much again, Professor Endo.
Thank you. Bye-bye.
And the second speaker, the next speaker is Professor Makoto Ikeda from University of Tokyo. Professor Makoto Ikeda is a professor with the System Design Laboratory, University of Tokyo. And his research interests include high performance, low power, and reliable digital circuits, especially for hardware security and smart image sensor design. Professor Ikeda received a PhD degree in EE from the University of Tokyo in 1996. And he is a program committee co-chair of the Cool Chips Conference series and also senior member of IEEE. So, Professor Ikeda, please start your presentation.
Thank you, Nakamura-sensei. Can you hear me?
Yes.
So, thank you very much for inviting me on this conference. Unfortunately, my talk doesn't include any non-volatile memory stuff, and also mostly my topic is to introduce the organization and newly established the organization. So let me introduce the my talk, Agile-X platform for semiconductor integrated circuit design and fabrication democratization. So before going to the Agile-X, I'd like to introduce the affiliation in short. So the name of the center is DLAB, as Nakamura Sensei have already introduced, and has been established the 1st of October 2019. So it's a very new research organization inside the University of Tokyo. And the purpose of the research center is to encourage researchers in design of LSI in the University of Tokyo. So we have been organizing the so-called the VDEC, VLSI Design Center, as a part of the University of Tokyo to provide a chip design platform among Japanese universities. But on top of that, we need to encourage the research itself. So that's the reason we merged VDEC function into DLAB. And the major activities in DLAB related to VLSI design is listed here. So basically, we still maintain chip design platform among Japanese universities, providing chip fabrication gateways to the Japanese universities and providing EDA tools to design chip. And also, we provide chip design education itself. Also, for past 5 years, we organized so-called AI Chip Design Center, which is joint activity by DLAB and ICE, Advanced Institute of Science Technology, supported by NEDO and METI, which is a funding agency of Ministry of Economy. And the mission of the activity is to provide design environment for smaller startups and smaller industries. It is just the industry version of the VDEC activities. And the unique function is we provide the chip verification functionality by the hardware emulators. So it is very powerful hardware emulators to verify the SoC design itself up to the software level. So, and the last one, but the most important one is activity is so-called LAS activities. And the LAS is a consortium led by the University of Tokyo with the larger industry in Japan for the state-of-the-art chip design within the advanced process node. So, basically, these are the three major design-related activities. Of course, we have the device level activities, including organizing a super clean room to provide the equipment to the Japanese applications, but I'll skip that. So coming to the main topic of Agile-X. So this is the background of why we propose the Agile-X, the chip democratizing the platform. So basically, all of you might know or agree that we have many waves in the semiconductor market. The older one was the home appliances like handycams and so on and so forth. And the second one, this is to make the physical space present. And the second wave is something like PCs, personal computers, which is a creation of virtual or so-called cyber spaces. And the third wave should be smartphones, which everyone can carry the virtual cyber spaces by themselves. And now we have the so-called digital transformation waves, which is highly integration of cyberspace and physical spaces. Well, the bottom graph is the misery graph of Japanese semiconductor market share. So 30 years ago, there are 5 companies in the top 10 list, but now there are only one company, Kioxia, is in the top 10 the semiconductor the market share. But we are really afraid of Japanese the market will be diminished in coming few years. So to cope with this kind of situation, we might to change the something. By the way, you might know that there is the serious energy crisis for digital transformation. Basically, IT equipment consumes twice of current entire the electricity consumption in year 2030, and it is expected to be 200 times in year 2050. By the way, I heard that the total amount of energy consumption by IT equipment in the world is already over the energy consumption of United Kingdom itself. So there are no sustainable digital transformation society without solving energy crisis. That is the underline. And why the energy crisis? It's coming from the AI. So everyone is now using AI or claiming AIs, but the computational complexity, because of that, the computational complexity of AI is expanded to 10,000 times for past 10 years. But the problem is energy efficiency of general purpose processors improves only 10 times. Although there have been a huge amount of contribution, just like Professor endorsed the contribution with the non-volatile memories and so on and so forth, of course, coming from the process technology itself. But even so, the improvement is only 10 times. So because of that, the energy consumption by AI is becomes the critical in the energy crisis in the entire IT. So you might always see this kind of the so-called Makimoto waves or something. So basically, there are the swing between the general purpose chip fabrication and the domain-specific or application-specific chip fabrication, which is mass production in general purpose and the small production in domain-specific production. So basically, for general chip or mass production, it starts with device innovation, like a DRAM or CPU or advanced process, and win by the capital competition. So basically, these kind of waves occurs for the specific chip like a DRAM, CPU, or flash or GPU, and so on and so forth. But now they are suffering from energy crisis. On the other side, for the domain-specific chip design, it starts with design innovation and afraid of end by the end of Moore's law. So basically, in the era of 1990s to year 2000, so-called ASIC has been boomed. But sooner or later, it is replaced by GPU by the end of Moore's law. But now, because of the energy crisis, we need to optimize the energy consumption or reduce the energy consumption by domain-specific or specified AI design, AI hardwares. And also, thanks to the slowdown of Moore's law, we expect that the ASIC era or domain-specific chip era will continue for a while. Everyone might agree that the issue of domain-specific chip design is the efficiency of design or efficiency of design fabrications. So basically, to design a specific chip, it takes huge amount of effort, labor, brain effort, as well as huge amount of time and cost. Also, it costs huge amount for fabrication. So to accelerate digital transformation, of course, we need to highly integrate the hardware and the software. And in addition to that, because for digital transformation, requirement changing quite the fast. So continuous updates of the hardware and software according to the fluid demands and environment change. So basically, people assume that it's not for hardware but for software. But the software requires huge amount of energy consumption. So to cope with that, we need to have LSI design as programming and LSI fabrication as compiling, just like a software. And updating hardware along with software to agile development and revision cycles. So accelerating the development or revision cycle should realize the huge amount of the advancement. Even the one revision benefit only 5% of the improvement, but if you can realize the revision in 1 week, then within a year, the advancement will be 100 times or more. So that should be the basic concept of agile design, agile chip design, or agile chip development platform. So we want to make the turnaround time of chip design and fabrication down to 1/10. And also just the same as the turnaround time, we want to make the cost to 1/10. And we expect to realize that we can increase the number of LSI designers, and which can make the LSI democratized. So our target future society is, of course, just as the Endo Sensei mentioned, the carbon neutral and inclusive society by the digital transformation. And for the desired ICs is that domain-specific chip by many people, many, with the rapid improvement cycle to cope with energy crisis for digital transformation. So again, the idea to chip turnaround time should be reduced down to 1/10. And cost also should decrease by a factor of 10. So we want to, under this concept, we want to realize the agile chip development platform. So basically, the most of the industrial people assume that mass production to optimize the chip cost. So basically, non-recursive cost increases. Sorry for very tiny characters, but by the process shrink. So, by the process shrink, manufacturing cost it becomes lower. So in total, if you have a huge amount of mass production, the current the process shrink is optimal. But on the other side, if you are targeting small production, it's not cost effective for the advanced process. So we need to think of something to cope with this to minimize the cost. Of course, to minimize the design turnaround time. So currently, design takes a huge amount of time, and of course, huge amount of the cost. Just the same for the manufacturing. But we want to make all of them in 1/10. So chip democratization has been claimed manywhere for past 2 or 3 years. And this is targeting the innovation by many designers. This is the interesting researches by the English researchers by the plotting the number of people in a small island in Southern Pacific Islands and the number of tools. So the number of people increases, the number of tools increases. So this means acceleration of technology improvement by mass brain. So many designers mean the acceleration of design technology or technology itself. So basically, the many people are going for that direction, and Google have announced the open PDK and free shuttle 2 years ago, and also Dr. Mark Liu, president of TSMC, also delivered a plenary talk last year in ISCC. By saying, by concluding from a few to many to accelerate the technologies. Also, there have been a huge amount of the discussion in the last Versa Symposium in June in Hawaii for design ecosystem or open source chip design. So we'd like to make silicon just compiling like this, GCC hyphen O silicon. This is taken by the Google, but the we have the same target. So many people were aware of the SoC design schedule. It takes more than 1 year for many cases from the starting from the higher level description and down to hardware description by the high level synthesis and physical implementation and timing verification and physical verification. So it's a long and time consuming and cost consuming process. So as I mentioned, we want to make this down to 1 week. How we can do that? Of course, we need to take a file for higher level description. But after that, the physical implementation or timing and verification should be within 1 week. And if we can fabricate chip within 1 week, we expect the situation might be drastically changed. But many people assume it is equivalent to FPGA. It may be true for some of the applications, but there have been many applications which the FPGA and ASICs are not equivalent. I have been working for encryption, cryptography, realizing the algorithm of cryptography onto ASIC, and there it is usually using higher radix numbers, and so optimal design for FPGA based on the DSPs inside and the ASICs are completely different, and so because of that, it is no more suitable for prototyping by FPGA. As I mentioned, the FPGA design, the optimum, and ASIC design optimum is completely different. And so, of course, you might assume that this performance might be good enough, but some people might need to improve the performance. But for using FPGA, you might need to purchase the expensive FPGA by the advanced process, which might not be so easy. But for the ASIC implementation, for this, we have realized, designed, and fabricated using the 65 nano. And the time and power consumption is something like this. And if we want to improve the performance, then we can just utilize the advanced process like 12 nano. And we have fabricated, and we could easily obtain the 3 times the performance improvement with 9 times the energy efficiency. So this is the power of the using advanced process. So once we can have the description for optimum design, then we can improve the performance by utilizing the advanced process. So high-level description is a key for the design time shortening. Of course, people might already aware of the high-level HLS for FPGA design and ASIC design. So we want to improve this one with the reuse the mechanism of design know-hows. For agile fabrication platform, some of you might know minimal fab, and by utilizing that kind of functionality, we could form the topmost wiring by only 1 day, and which makes the fabrication time quite short. Of course, the minimum fab the capability is not so enough, so we might need to use advanced process. So for that, we also utilize our super clean room fabrication lines for the advanced process. But anyway, to using our Agile-X, then we expect to increase the number of chip designers or digital chip designers by a factor of 10 because there are a bunch of the software designers. I expect 10 times more than the current hardware designers, but they are completely isolated at this moment. So software designers have been working for service development by the general purpose chips, which consume huge amount of power. But if we, the software designers, can become a hardware designer or digital chip designers, then software designer can also write out the C code or Python code to realize a domain-specific chip, and which makes the services the much power efficient, and also because the hardware development cycle becomes very shortened, then we could update the services itself by this kind of agile design ideas. So we gathered the many researchers inside the University of Tokyo, ranging from the device side up to the application side. And we formed the two platform development researches and 8 domain research domains ranging from IoT, AI, the communication, security, sensor, energy and device, and biomimic circuit. So they are the user of our Agile design platform to realize their algorithms or to somehow interface their devices and so on and so forth. Of course, once the platform is ready, then we want to expand the Agile-X idea to nationwide through our VDEC network among the Japanese university to realize real chip design and development democratize. And hopefully this will attract many designers to Japan to somehow change the next the chip design paradigm. So I expect more to come in very near future. So this is the end of my talk, and thank you very much for your kind attention.
Thank you for the great talk. So if now this session is open for questions. Is there any questions or comments? Ikeda-san, can you read the chat?
Yes. So which one should be the first? Oh, okay. So the first question from Tanimoto-san is how to fill the gap between embedded software code and code for higher level synthesis. So that's the very important and difficult point. But we are now trying to realize. By the way, everyone might know that there have been already very sophisticated higher level synthesis tool for FPGAs by utilizing their bunch of IPs. So we want to borrow the idea or fundamental ideas for such kind of tools, and we want to realize the the higher level synthesis. But of course, the still current the higher level synthesis is having a huge gap among the pure software and description for higher level synthesis. So we are now working towards that. Sorry, I have not so clear answer for this one.
Okay, the last question is what's the most challenging issue on designing AI chip accelerators?
So basically, everyone agrees that the AI algorithm itself advances day by day, but the chip design takes 1 year. Then once the sophisticated the AI chip is available, then at that time the AI algorithm is far advanced. So that should be the one of the biggest issue at this moment. So for that, if you can realize your current up-to-date algorithm in say the 2 weeks, then you can catch up the most advanced the algorithm by hardware, which makes great advantage. So that is the basic fundamental idea of our Agile-X. But the besides that, the challenging issue, there are many challenging issues. One of which should be verification. So basically, of course, you might agree that it's just an array of huge numbers of the processing element, or I don't know, what you call neuron or something. But of course, you can verify each processing element, but it often causes the communication jam, which makes the your performance very slow. So to avoid that, you need to verify the architecture by for the corner cases or worst cases. So for that, I assume that I'm sure that the hardware emulator works for evaluating that kind of situation. So you need to evaluate all entire chip. It means the huge amount of hardware by very long test cases for verifying the corner case, which should be the challenging thing.
Okay, thank you. So since the time is running up, so thank you, Professor Ikeda, and we'd like to go to the next and last talk of this session. The last talk of this session is by Professor Hitoshi Wakabayashi from Tokyo Institute of Technology. Professor Wakabayashi received a ME and PhD degrees in EE from Tokyo Institute of Technology in 1993 and 2003, respectively. He was with NEC Corporation from 1993 to 2006, and from 2000 to 2001, he was with MIT. And in 2006, he joined Sony Corporation, and then since 2013, he has been a professor at Tokyo Institute of Technology. So, Professor Wakabayashi, please start your presentation.
Thank you very much, Nakamura-sensei. Can you hear me?
Yes.
Thank you very much for your kind introduction. My name is Hitoshi Wakabayashi from the Tokyo Institute of Technology. So thank you very much for the inviting me as one of the speakers of this very special invited session in the NVMSA 2022. And let me show you the today. So let me have an introduction and 2D FETs for the logic, not only for the memory, and ferroelectric characteristics in the hafnium oxide as a ferroelectric material, and the new activities named as a integrated greenics in the as the same as the previous two speeches, and finally conclusions. And so this is a kind of my the point of view. I'm now targeting the context computing society that builds the trust through our industry, and for the consume the COP, the green transformation and green tragedy, and also the COVID-19, DX, and so on. And based on this kind of a demand, so let me show you our industry of the growth. And this figure shows the number of the transistors depending on the years. And as you know, the TSMC fabricated so many the processors such as Apple M1 chip and M1 Max and M1 Ultra. And if you see the that slope over here, so you can find the so high slope of the the progress much higher than the Moore's law slope. And based on this demand, so we need to accelerate the research not only for the non-volatile memory but also the logic. And let me show you the logic progress currently and fabricated by the reported from the TSMC here for the 5 nanometer silicon germanium fin. And as everybody knows, the 5 nanometer FinFET fabricated with the silicon germanium channel for the fin and silicon fin for the N. And based on those type of the technologies fabricated by using the EUV lithography, the characteristics itself is much better than we expect, such as not only for the static IV characteristics, but also the sort of the parallel curve of the SRAMs and so on, and also the variability too. And also currently we have some report from the Intel Corporation named as Intel 4 in the VLSI technology 2022. And reported on the FinFET with this type of the very small size of the fin, and also the so many technologies inside the Intel 4, as almost same as the 5 nanometer TSMC. Especially in this paper, they disclosed about the actual parameters and the characteristics of the IV curves for the FinFET. And let me show you the benchmark of this device. And the right figure shows the harmonic mean of the V over I. This is a transistor, the on resistance for the N and P harmonic mean, and depending on the publication year. And open circle means the so many papers from the many companies and institutes. And the blue dots shows the dots reported from the only Intel Corporation, and including the Intel 4 and 10. And those type of the dots achieved by the Metal-Gate High-K and the Strength Silicon and Metal-Gate High-K and the FinFET here. And after the Intel 10 nanometer of using the FinFET, we can see that so many huge the progress of in the Intel 4 as compared to the Intel 10 nanometer here. And that means the Intel 4 has so much the taller FinFET with the high mobility channel, I think. And after that, Intel prepared this type of the 4 stacked GAA nanosheet FinFET FETs. So therefore, we can expect the so huge progress of the Intel Corporation, I think. And this is the progress of the logic scaling. And this is a technology node depending on the years, and including the Samsung 4 nanometer, Intel 4, and TSMC 5 nanometer, and Samsung 7 nanometer. And if you see the area of the 60 SRAM, depending on the years, the Intel 4 is almost same as the Intel TSMC 5 nanometer here, like this. But 2 years later, and this is so along with the not the 0.7 powered by 2 per 2 years, but also the 1.8 powered by 2 per 2 years here. And along with this the trend, so we can find some sort of the progress of the circuit, I think. And this is also the progress of the depending along with the technology node for the companies. And as I said, the TSMC has a so huge good progress of the technology as a silicon germanium fin. And even in case of the Intel Corporation, have a so huge the progress of the current based on the taller fin and the high mobility here. And after that, so we can expect the nanosheet FET or 2D material like this. And this is a report from the TSMC in 2022 VLSI symposium. And Dr. Mi reported on the both side interconnects for here like this, and also their expectation on the 2D material of the TMD named as a transition metal dichalcogenide. This is a new material of the semiconductor channel in the logic LSI, having the two seed structure of the material, not only the bulk type of the material. And after the FinFET, so nanosheet and the CFET complementary FET that stacked among the NFET and PFET. So they expected to see the next generation rather than FinFET. And after that, the TSMC and me too, so expect the 2D material of the channel and then the carbon nanotube and so on and so forth. And so firstly, let me show you the CFET structure. So this is our report on the stacked CMOS among the NFET and PFET. And this is a half of the 60 SRAM like this. And then this is the structure of the circuit. And so having considering with the self-heating effect inside the nanowire like this. And as you may know, the size of the area is aggressively decrease with having this type of the structure. And then let's see that this is a kind of the fabrication processes of the stacked CMOS structure. And this is applicable for us for the fabrication, I think. And nextly, let me show you the far from the now. So for the 1.5 nanometer technology node here. And if we find this type of the regime of the 2028, so we can expect the 1.5 technology node and having sometimes the 4 nanometer gate length like this. So this is some sort of the scaling limit due to the source drain type tunneling here like this of the gate length of the 4. And in that case, we need to reduce the channel thickness of the channel down to the 2 nanometer here. And if we see this type of the structure, so this is a mobility depending on the body thickness here. And so if we see the 2 nanometer body thickness here, if we use the silicon or bulk type of the semiconductor material, so we need to consider about the mobility degradation here. And less than 2 nanometer, so we already find this type of the new material with the high mobility, such as named as transition metal dichalcogenide, TMDC or TMD. So especially as MOS2, tungsten disulfide, zirconium disulfide, and tungsten diselenide and so on. If we see this type of the cross-sectional image of the channel, here is the 2D material of the MOS2 film, having the sheet type of the material here, less than 10 nanometer or 5 nanometer channel thickness here. And this is atomic structure of the MOS2 film. And so we expect that this type of the material for the next generation technology node here. And the Intel Corporation is also reported on this type of the FETs like this. Almost same structure itself is almost same as a nanosheet, however, using the 2D material here. And Intel reported already reported on the double gate of the 2D FET here like this, and also the ivory curves too. But the performance itself is much smaller than we expect here. This is our results using the MOS2 film, but this is a single gate. However, this is a very state-of-the-art structure of the 2D FET, having the very new type of the technologies such as isolation and so on, contact structure and so on. And having the 2.5 nanometer the thickness of the channel using the MOS2 film. And also so based on this type of the material, and also the thickness, the thin film thickness of the channel. So we can find the very small size, the level of the off current, and also the good number of the threshold voltage here. And nextly, let me show you our result too of the tungsten disulfide of the PFET. And this is the characteristics of the PFET, and also the mobility, the histogram of the mobility like this. And even if we use this type of the new material, so we've already fabricated this type of the array structure of the device, and also the histogram of the mobility like this. So based on the very small state-of-the-art, the structure of the device by ourselves. And this is the material of the zirconium disulfide film, having the very high number of the mobility in the Hall effect mobility in more than the 1200. And also this is the structure of the device of the hole and the electron. And we expect the good the benchmark of the device rather than the Intel FinFET like this, with the small number of the on resistance and also the power density here like this. And also to fabricate the nanosheet for the 2D material for the nanosheet, we've already fabricated this type of the structure with the contact technology. And let me switch the gears a little bit about the our impact, our consideration on the green society. So if we consider about the environmental impact reported from the IMEC, this is reported from at the conference of the EDTM. And if we see the right-hand side figure of the figure, this is the number of the steps of the fabrication for the generation of the 28 to the 3 nanometer technology node. And as you know, the number of the steps are rapidly increase with decrease in the technology node like this. And also the energy use also the increase with decrease in the technology node, and also the mainly consists of the lithography energy and also the dry etch energy. And based on those type of the analytics, the energy used depending on the technology is rapidly increased with this like this. So therefore, in order to reduce this type of the energy, if we consider about the greener society, so the 2D FET needed to be achieved, I think, to reduce the not the etching energy, dry etching energy at least like this. And in order to understand, to consider the life cycle assessment of the semiconductor industry, so we need to discuss about the functionalities of the LSI. This is a whole bunch of the functionalities inside the chips and also the devices. And let me show you the two types of the technologies for the energy harvester and also memories. And if we see the memory, so if we find the switching energy benchmark reported from the Intel Corporation, this is the switching energy depending on the delay here. And so the dashed line means the energy delay products. And so if we find the bunch of the dots are based on the CMOS the switch here. And here is the red one means the magneto-electric switching, and the yellow one means the ferroelectric the switching devices. And as compared to the magnetic type of the device, so we need to focus on the ferroelectric the material to switch rather than as a memory like this. This is a ferroelectric endurance of the ferroelectric material of the hafnium oxide on nickel silicide. No, it's a nickel silicide. Silicide, the electrode reported from our side of the Tokyo Tech, and having the so good number of the cycle, the endurance like this. And furthermore, we reported on the high endurance of the hafnium oxide on with the cerium oxide as the source of the oxide like this. and achieved the large number of the switching cycle like this, based on this type of the ferroelectric the structure and the characteristics. And based on those type of the structure, the techniques, we are now trying to fabricate the FERAM like this. This is another things using the thermoelectric generator using the ZVEC device, and reported from the Tokyo Tech like this. And this is the right hand side means the tungsten disulfide ZVEC coefficient, and also the MOS2 doped by the niobium like this, having the so huge number of the ZVEC coefficient. And based on this type of the technologies, we can fabricate this type of the systems to consider about the life cycle assessment to achieve the greener society. And let me show you the fabric of the device. So this is reported from the University of Missouri, Kansas City, in the 2017. However, so this type of the fabrics, the related having the stack type of the NP and NP type of the transistors, and also the by using the appropriate insulator in between the devices. So if it's sometimes for example of this type, if we insert the insulator here, so we can fabricate this type of the inverter by using the stack type of the device, and so on. So we fabricated the variety types of the structures and the circuits fabricated by using this type of the 3D fabric structure. And also I'm now thinking about the normal type memories in between the circuit level LSIs like this, in between the logic here. So almost same as in-memory computing or something. And also not only for the chip circuit level, but also the transistor level needs to be fabricated inside here, like by using the normal type memory node in between the small size of the LSIs. And those type of the structure can be fabricated by using the 2D type of the film transistors. And just like film, so we can fabricate a very thin type of the device, even for the 3D structure type of this type of the fabrics. And in order to fabricate or achieve this type of the structure, so we are now controlling the new type of the project named as integrated Greenix. Integrated Greenix, supported by the MEXT Japan. And the information itself is disclosed just only in Japanese. However, I'm very sorry about that. But let me show you our website here. Here is the website of the integrated Greenix, and led by Tokyo Institute of Technology with the Toyohashi University of Technology and Hiroshima University. And we have 30 researchers from 9 universities and institutes, and 21 companies among our project. And we welcome you even now. And also the goal of this project to make semiconductor industry greener. This is our goal. And please visit here. So you can find the integrated Greenix. And this is our researchers in those type of the institutes and also the companies here. And not only the integrated Greenix. So I'm now doing the three types of the consortium control like this. The first one is the ISSM consortium. So this is the Research Center for the Earth Inclusive Sensing with silent voices, and basically supported from formerly supported from the JST COI program, and then we are now controlling the independent consortium in the Tokyo Tech. And also another type of the consortium named as Industry University Consortium for Integrated System to Materials. And this is based on the program, JST program named as CREST and PREST. and named as the information carriers. And this is the integrated Linux, as I mentioned. So those type of the consortium needs to be collaborate each other by using the concept of the collaborative research among those type of the consortium, not only for those type of the consortium, but also the other outside from the Tokyo Tech. Let me conclude my talk. The 2D fabric LSI with a non-volatile memory in integrated Linux are discussed like this, and supported from the XNIX of the next. Thank you very much for our talk, your time. Thank you very much.
Thank you very much. So then this session is open for questions. So is there any questions? Can you see with the chat, Wakawai sensei?
Last one. I mean, the challenge on the reducing the size of the filter based on the chip, because of the big challenges might end up to serious acting the yield ratio chip mass production. So in the case of the so of course you're right. So in order to achieve this type of the yield, and also so in order to control the material, and also the not only for the initial characteristics, but also the endurance and the reliability and so on. So we need to add another technology such as sodium oxide or something to control the characteristics and the yield, reliability and so on. So this is another, so that's why, so we are now trying to fabricate this type of the large size of the FERAM with the higher yield, and also the with the collaboration with the companies for the mass production. This is our current stage. But so many institutes and universities are now trying to fabricate this type of the ferroelectric the memories through the several companies, I think. This is our situation for the non-volatile memories.
Okay, thank you. Is there any questions? If there's no question, then almost we are on time, so I'd like to close this session. So the wrap-up is 3 talks include world-leading results on materials and device, but also an effort on system and design. Because the target of this symposium is non-volatile memory, but with the emphasis on systems and architecture. So I hope you enjoy this session. And following my remarks, I've heard that there are some concluding remarks from organizers. Is there any message from the organizer? If there is no message from the organizer, then
yes, the organizer is coming up.
Okay.
Okay. Could you hear me?
Yes.
Yes. Okay. Thank you, Professor Hiroshi Nakamura. This is Ren Wei-xie, the General Chair of NVMSA this year. Thank you all to attend NVMSA 2022. Although we have a hybrid conference this year, the number of online attendees reached the record high this year. And next year, NVMSA will be held in Japan, and we are very possibly to have a physical conference again. So look forward to see you all in Japan next year. Now I conclude the end of NVMSA this year, and see you in Japan next year. Thank you very much.
Thank you so much. See you.
Thank you very
See all of
much.
you in Japan next year.
Yeah.
Thank you.
Thank you.
See you all. Okay. Okay. Bye-bye. Thank you. See you next year.
See you.
Bye-bye.
Bye. Bye-bye.